Morning, everyone. A, I think today we can finish the matrices. Maybe we can go to the eigenvalue, but let me review the last part of our discussion, which is the inverse of the matrix. And also, I will show you how we can also operate the inverse, or how to find the inverse of the matrix using the row operation. So we have this method with the adjoint, which it can be a little bit if we have like a more than 3 by 3 size matrix, maybe it feels that you are going to find like each of the covector all the determinant. So if we have 3 by 3, at least we have 2 by 2 determinant that we need to find for all the 6 or 9 covectors. And then we need to transpose all of them to make into our multiplications with the 1 over determinant. So it will be a little bit of trouble if the number of sizes is increasing. So for example, if this is 4 by 4, 5 by 5, although the method, this adjoint method, it still works. It still works for the square matrix that has the same size for m and n. But for maybe matrices with different sizes, or perhaps not squared, well, maybe there will be no matrix because no inverse of the matrix because maybe it will be a singular. But let me go through just one example here. So basically, to find the inverse, we need to compute the determinant, right? So I think we can try one by one here. So determinant, let's say this is, let's name this A. And I will choose the, or let me write the signs first. So determinant A is equal, we'll start -3. And then 0, and then +2. Right? 2 negative, yeah. This will be -3 multiplied with 0 minus 5 is -5. And then +2. 8 minus -1, right? 9. So 15 plus 18. Is that correct? Let me know if there's any mistake. I haven't calculated yet, so I'm just doing it now. If you see any mistake, let me know. Right? And then finding all the covectors. Let me just do it one by one. Okay, so covector 1, 1. And let me erase all this sign here. It's confusing with my calculations. So 1, 1 is 8, right? C1, 2 is 0 minus 20, right? C1, 3 is 2. 2, 1. Or row 1, row 2, column 2, column row 2. Should be 2, 2, 1 here. Wrong, right? Should be 2, 1. Row, column, right? Yeah, sorry. Okay, so row 1, column 2. 0 plus 2, so plus 2. 2, 2 is minus 5. Minus 4, minus 15, minus 19. And then last one is 12. And this will be 9, right? Zero minus 3, so 3. Is there any miscalculation? It's okay, right? Which one?
The first determinant A.
Oh, yeah.
Minus 3.
Minus 3.
Should they be minus 1, 9, and 4, 0?
Oh, yeah. Good. I picked the wrong determinant, sorry. But the second one, okay, right?
Yeah.
Okay. Minus 1, 5, 4, 0, right? Okay. So this should be negative 3, negative 20, right? This should be, it's correct, right? This one is correct. So 78, right? And how about the cofactors? Is there any mistake? Usually I just input into the software and I get the result directly. I think if you want to like compute really fast and make sure that your calculation is correct, if you use MATLAB, I think it will be faster. So inverse is 1 over 78, and this will be 8, negative 20, 2, right? 2. Okay, and then you can just stop until that. And one of the property that is our I think that will be our principle for the inverse of the matrix is the n by n matrix. Let's say A is non-singular if the determinant A is not 0, right? So I think I think last week I also explained a little bit about this. So what this means is, because matrix, you can imagine a matrix system like a maybe a system of factors. You can imagine like a factors. So what singular means is your bunch of arrows of the factors, if you have singularity, they are going to be into a single point. So usually that means that your value will be your determinant value will be 0. Okay. And if it is non-singular, it means that the determinant is not 0, which means that you can still have your direction of the vectors. Okay, you can let's say you can imagine like a vectors, like a system of the vectors. And now if this happen, okay, then if we take this and we take this multiplications, this should allow us to get into our identity matrix, okay? Because they're simply invertible with each other, which means that the determinant, so this will implies, or let me write in the right side, this will implies that the determinant of A and determinant of A inverse, if we multiply, this should be the same with this, which also gives the determinant of the identity. But since, okay, let me write here, since the determinant of I is 1, because the diagonal matrix is 1, so we just multiply the diagonal matrix 1, right? And then the product for the determinant A inverse, this is going to be also 1, which is not 0. So we have the non-singular property. So we could also rewrite the statement. So we can write an alternative way to write this is the n by n matrix A. This will be singular if and only if that the determinant A is 0. Okay. So first is we say that this will be non-singular, that if the determinant is not 0, but it will be singular only if the determinant is 0. Which means that the determinant will be your first procedure or first operations to know whether the matrix has an inverse or not. And on the next page, I will elaborate this property. So we can say that if we are going to multiply a matrix with its inverse, we are going to have the identity matrix. Okay, the identity matrix, I think I will write on the right side here, just to give some idea that the identity matrix is, for let's say for 3 by 3, okay, this is identity matrix. If we elaborate in row operations, this 1 1 1, the identity, it could be also our variable of the solutions that we find when we do the row operations, when we subtract, multiply, and then we make it all 1 1 1, and we could have all variables. Each variable has each solution. Right? And that's the idea, actually. What we are going to do with the inverse, we are going to involve the inverse, involve the identity as a parameter to find the inverse of the matrix. Okay. Okay. Let me go through. Or do you want to write first? Okay. I think you can write this first. Have you tried like AI tools to compute some math problem? Have you tried? No. I tried because last couple of months I tried the paid version. It's doing good, but sometimes for a typical like for straightforward questions in math, like in calculus or maybe in engineering math, he can answers like perfectly, showing you the code, the Python, how he compute and analyze, and he gave his own analysis. But when I try some polar equations and then I give them the calculus problem, I think he did pretty well at the beginning. He shows the procedure, which is correct. Oh, finding the intersections, the angle, blah, blah, blah. And then when he start doing the Python, he start calculating. He find so I'm asking the area between the curves, and he find the area is negative, which he, at the next step, he denies that negative. Oh, this could be some misrepresentation. And then he calculate again, and he got negative. And he doing it like, so he calculate and he denies. He calculate, he denies. I think after 4 repetitions, he gave up. He gave up at the end. I can show you later. So he gave up at the very end, and then he just like maybe there is some mistake, blah blah blah, and then he just give up. And then I help him. I help the AI. Oh, you need to do with symmetry. You can multiply this by this. And then he, oh yes, I will multiply it, and then he got the correct answer. It's pretty funny. Maybe I will make something out of it. Maybe our course. I think I'll try if he can solve. Okay, and interestingly, he can compute using some code. So we can also check if we know how to code. We can also check with the code whether it works or not. Okay, now get back to this. So the row operations that we did, we could try the inverse, finding the inverse. So let me go here. So let me just showing you that the beginning is, so basically what we did is, so we have the property A multiply A inverse is identity, right? So what we want is, we multiply each one of the side with the A inverse, or so let's say if we multiply this with the A inverse or A, okay, so maybe I'll explain this one first. If the n by n matrix can be transformed into the identity by sequence of elementary row operations, basically what we did previously, we take one by one, and then we get this identity, so 1, 1, 1 as our variable of solutions, right? And then if we want to make some sequence in the inverse, okay, of the matrix A, we can also transform matrix A into the identity. So what do we do is, this is supposed to be our original matrix. This is the identity, right? So what we do is that basically we want this, the left part, to be 1, 1, 1, 1, to be identity. And when we're doing this, we could also transform this, because this will be our first row, this is the second row, and then this is the third row, and so on and so forth. So when we make this into identity, we will get this right side is the inverse. You get my idea? So we take the left part as our matrix. This is the identity. Okay. We want to make the left part is 1, 1, 1, 1. And anything happen that on the right side, that will be the inverse. Okay, so I think this will be very interesting and very, very, I think, compared to the previous method, the adjoint method, maybe will be faster, because you can do the operation one by one easily. If you use the previous method, I think sometimes you will have some trouble if the number is not really a whole number. Maybe it's a fraction or decimals. It's maybe not very good. But here you can avoid those mistakes by taking into the row operations. Okay, let's see what we do here. Let me give you an example. So basically, let me write here. What we do is basically we will have A, and here is the identity. Okay, so this will be our original matrix. And this will be the identity. So our goal is we take this and make some row operations. And the end, okay, the goal is we get, this will be identity, and this will be the A inverse. So practically, if we see our original equation here, we just need to multiply with A inverse, and we get that the A should be A, sorry. So this should be, it should be the same A, right? It goes back to the original equations. So that's what we do. So we are going to take the row operations and make it into the identity. Okay, now example, we could try this one. So we could write, first is taking all of this, 2, 2, 0, negative 2, 1, 1, 3, 0, 1. And, oh, sorry, should be 1, 0, 0, 0, 0, 1, 1, 0, 0. Okay. Now let's do the row operations. Maybe left here. Okay, this one. Maybe first is taking the half of this. And maybe I'll write one by one. Okay. Maybe 2R1. So 2R1. Maybe wait. Or maybe 3R1, 3R1 minus R3. Oh, this will be the new R3, sorry. Let me put here. This is R1. Let me just write 1, 1, 0. The second one is three over two. Three over two, so this will be 0. 3 over 2. And then 3 over 2, 5 over 2. Right? Okay, and then 3R1, 0. Oh, maybe not good path. Let me just think another path. Maybe just keep it for a while. What else should we write? Okay, maybe we could have, maybe R2 is 2 over 3 R2. And the R1, the new R1 is, we can multiply with 3 over 2 minus R2, right, to make it 0. So we have 3 over 2 0, 0. 3 over 2 is 3 over 4, 0, 0. And then the second row, or maybe let me just compute first and then multiply. R2 maybe just maybe multiply. Okay, this will be 0, 1.
Professor?
Yes.
Excuse me. So if we do 3 over 2 R1 minus R2, won't the third member of R1, which is 0, won't it be like 0 minus 5 over 2? No?
Oh, right. This should be. Wait, is this works? I haven't checked the final result. Let me check the final result first, okay? Let me check first. So to make it fast, and so let me open my MATLAB. I'm afraid maybe we are not getting any answer. And maybe I've put the wrong equation. I'm sorry. Okay, I think correct, right? Ah, okay. No, inverse. I think I get it. Yeah, wrong inverse. Oh, suppose. Oh, wait. I haven't make it. I haven't delete all this. Okay, let me make the a. Wait. Wrong command. 220.211.301. Oh, no, I think it's correct. Okay, we should get, yeah, should be. So let's work this out. So anyone could provide me faster solution, or let me change the equation. I put the wrong equation actually. It should be the other one. Okay, let me get through this. Okay, so we have this. Anyway, how about I will put this for a while. So let me get to this later, okay? And maybe let me just make it a new page. I should give you this instead, but I want to work on that. Let me just write this. Okay. Or if you want to work out later, that should be okay. But I think this should be done. Okay, I think we can work with this. We can work, I think the top we can multiply first, and this, so my suggestion is you try to do your row operations to make it familiar with the system, because there is no clear like right answer how to do it, which path you should take, because every possible path is okay, as long as we can came to the, or we can get the final result. And then let me just write his first. And then what else? I think we can do the 2R1 plus R2. So far, okay. And we can make the R3 plus 5R1, right? This will be 0. 5/2. 5/2 plus 12. 12, 17/2. Five over two. Right. Now I think the second row and the third row is ideal for the next step. So could take 1/3 and we could take the 1/5. So 0, 1, 5/3, 1/3, 1/3, 0. 0, 1. Wait, this is 5, 5, 1/2. Okay, now it's become ugly. Okay, we can have this. I think we can take the below equations, make it 0. We could just maybe the last one, last row, maybe just take the subtraction between 2. So we have 1, this will be 0, 1, 5/3. This will be 0, 5/3, 5/3 minus 17/10. So my negative 1/30. And then 2 minus 1 negative 1/6. Right? I think we can just multiply with negative 30 to make it positive 1. Okay, 1, 0. Okay. So this will be 5, negative 10, and 6. Okay, so far so good. And we can remove the R1 and R2, the third column, by subtract to the third row. I think this is clear now. This one is clear. The previous one I will compute later. So new R1 is become a 2R1, right, minus R3, and the R2, new R2 will be 3/5 R2 minus R3, right? So R1 becomes 2, 0, and then 1 minus 1 is 0. This will be 1. Two R1. Oh wait, wrong. 2R1 minus R3. So 1 minus 5, negative 4. And then 0 minus 10, so 10 and negative 6, right? And then this will be 0, 3/5, and 1 minus 1, 0, 3/5, 1/5 minus R3. So negative 24/5. And then plus 50/5, right? So 51/5. And then negative 6. Is this correct? Which one? Which one?
The R2.
The R2 should be 1/3. Oh, so sad. But 6. This is 6, right? Okay. So wrong. Is it 1/3? Oh yeah, 1/3. Yeah. So careful when you write. I think this is 5, so this is 3. Okay. Okay, so 3/5. 3/5 is 1/5. Yeah, it's correct. 1/5, right? We multiply 3/5 minus 5. So this will be minus, sorry. Minus 24/5. Okay, now. And then minus 10. Minus 10 will be plus 10. So 1/5 plus, yeah, it's correct. 51/5. Yeah. Okay. And now we can get the final result, which we have our fractions. So R1 we can multiply with half, and R2 we can multiply with 5/3. So 1, 0, 0, negative 2, 5, negative 3. And this will be 0, 1, 0. 24 divided by 3 is 8, right? 8. 8. 51 divided by 3. It should be what? I lost in my computation. 17. Oh, 17. Okay. Finally, this is the inverse of A. Okay. After a lot of process, we finally get. So I think I from my point of view, raw operations, it's a simple process, but it takes time. It takes time, and you need to be careful on your own computations. Okay, it's very simple, but you need to like write really long calculations. Okay. Because you have like a really long matrices, and you need to careful with your own computations. Okay, we will have a break and we'll continue later. So determine A3 52 13. This will be 4. So this will be our solutions. Okay, so we have our solutions now. So this is another way to find A solutions, and I will just showing you this, although there are some proving, but I will skip that. This is another way to solve solutions for system of equation, particular on linear equations. Okay. So to solve the system, you can use Cramer's rule. You can use the inverse. Okay. You can use the row operations, the Gaussian eliminations method. They are all the same, and I think I will leave any methods if it's not directly asking which method you should use. Okay. If the question is asking solve the equation, so you can choose whatever method you want. Okay. If you prefer this one, I think you could check. I think this is also quick, also fast. Although you need to find the determinant one by one. And you could check the row operations if you want. That's also okay. Or using the inverse. Okay. Usually the question will be including the instructions. You need to use blah 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 method. Okay. Like use Cramer's rule to find it, which means that you need to get into the Cramer's rule. Okay, so I will just skip this. Okay, it's just a overview, and because we have this previously, the Cramer's rule. So let's go to the what we call the eigenvalue. Okay, and this will be an introductory. After we did this, we are going to go for system of differential equations. So we are going to solve differential equations using matrix. So let's see the definition first. So if we have some matrix A, like it has some sizes, the same size square matrix n by n, and we have K, which is the, so let me write here, I think it's still not defined very well. So let me write here. So A is n by n, and then K is n by 1, okay, matrix. So we have a column vector. This is column vector. Then we have the multiplications for AK. That will be a matrix AK that is defined, and it will be another, so AK will be another n by 1 matrix. Okay, so A is n by n matrix. So if we multiply A and K, you will see that it will result in n by 1, right? So we are going to find whether there are some n by 1 matrix K. So we are going to find this K. So this is K axis such that the AK is constant multiple for K. Now this constant, we call this constant is the eigenvalue, or we write as lambda. Okay, so when we have the system here, let's say A is the square matrix n by n, and we say that there will be a number that we call this number the lambda as the eigenvalue of A. So this will be a scalar, as constant. Then when we have A, there will be some K vector. We call this K vector is the eigenvector that is satisfy this equation. So AK equal lambda K. Now the solution for the K itself is this will be named as eigenvector, which correspond to eigenvalue. Now before we go into like how we find it like in the equations, first of all, let's just take some example how this going to work in a system. So we need to verify, let's say we have a K, which is the column vector, 1, negative 1, 1. This is just an example. Okay? We can have any number, but this number is specified that if we check, if we can find whether this is satisfied, that we could have our eigenvector and eigenvalue, which is verified within the system. And we have this 3 by 3 as matrix A. Now, if we want to check, then we are going just to multiply. So we multiply AK so we multiply all. 1 minus 3 is negative 2. So 2 minus 3 minus 1 plus 3 is 2 minus 2 minus 2 minus 4 plus 1 minus 2 plus 1 minus 2 plus 1 is minus 1 minus 1 minus 1 negative 2. Is it correct? Oh, negative 2, 3 plus 1, negative 3 plus 1, negative 2. Okay. And then from here, since we know that we have the eigenvector here, we can factorize the scalar. We can factorize 2 or negative 2 to make it into 1, negative 1, 1. Now this number negative 2 is our eigenvalue within the definition, okay, with our definitions. Now, if we use the property in our matrix algebra, we are interested in, let's write as A minus the constant eigenvalue multiplied with the identity, okay, which equal to 0. So where E or I is the, let's just say, multiplicative or identity matrix, okay. Now we let K as a, let me write here, let K equal a column vector or column matrix, sorry. So if we write using these expressions, then we can write the whole thing becomes this. So that. So each one of them will be having the minus the lambda for the identity, and because this is only the identity, so it's only work for this diagonal matrix. Okay. So we could write in that term, and finally, when this is the homogeneous, okay, so since this is homogeneous and we already have our definition on homogeneous, so let me write this is homogeneous. So in homogeneous, it has non-trivial solutions. If determinant of coefficient matrix or A is 0, or we could write here that we need to make this equal to 0. So if you want to find the eigenvector and particular eigenvalue, we need to have this determinant equal 0. Usually we say this equation, another name is characteristic equations of A. So later we see that the determinant, because in determinant we are going to have some calculations. So if you imagine like 2 by 2 or 3 by 3, which includes 2 by 2 matrix, they will have at least some multiplication. So if we have multiplication of, let's say we want to have the variable inside the matrix will be the eigenvalue. So the eigenvalue will be multiplied, right? And so at least you will see a polynomial. You will see a polynomial. So we'll see lambda squared plus something lambda plus a constant. If you check all the determinants, and you are going to solve this equaling 0. So it's actually either quadratic equation or maybe more than quadratic, or you can say polynomial. So you can also say from these characteristic equations that the eigenvalues of A are roots of characteristic equation. So we can solve the system by taking this and perhaps maybe row operations and find the eigenvalue and eigenvector. So that will be next week discussion. And actually, I will have some overview. What is actually the eigenvalue and eigenvector? I will show you maybe using some visuals to make it like to get the idea correctly. I think it's better to be understood using vectors. Okay, you have a vectors, and when you move the vectors, when the vectors, like you have two vectors, and you need to find in which way that they are going to be having the eigenvalue and eigenvector. That is when they are going to be their determinant using this is going to be 0, and you will see that it's actually a scalar multiplication of the eigenvector that can make that happen. Maybe that's for next week. Okay, any questions? No? If not, then I will ask you. Okay. So we are going to see. So basically, your quiz, maybe it will be focused more on linear algebra. Okay, not the eigenvalue. Okay. So before eigenvalue, the algebra part, the system of linear equations, the row operations, the matrix inverse. Okay, so basically linear algebra. Okay, so linear algebra.
And this is not linear algebra?
This is actually linear algebra, but for your quiz, we are not going into this. Okay?
Not yet.
Not yet. Not yet. Not yet. Okay.